Okay, so I thought we would take a little bit of time here to look at some of the application problems that you have assigned that you would be ready to do now that we've gotten through all of the practice problems for Module 5. So the practice problems that, I'm sorry, the application problems that I have for you are going to be found on pages 174 to 178 in your McGraw-Hill ebook, okay? So, so what I'm going to do is I'm going to grab these underneath my camera. And then we'll kind of go through and make sure that you have, a good understanding of how to get started on each one of these. So underneath, so 4.1 is our first problem. And 4.1 is found on the top of page 174. Okay, 174. So what I want to do is I want to just take a little bit of time to make sure we've got good free body diagrams for each one of these. Okay, so so why don't we go ahead and draw the free body diagram for 4.1. Now, my plan is not to work through each one from start to finish. It's just to make sure that you've got some good notes, and I'm going to give you some hints on next steps, and then you can finish up the problems, as you have time. So here is the illustration for 4.1. So go ahead and draw the free body diagram as you feel it would be for 4.1, and then we will compare and make sure you've got everything you need. And then we can, kind of talk about reactions at supports and stuff. Chris, I heard you're a free agent. That's what Christian said. Maybe I shouldn't have let you guys go. You might find something else you like better. I can't imagine that being possible, especially when you have statics this term, right? Right. I hope.
More fun than the luxury.
I've told you guys this before. I'm a big fan of statics, so actually I like it. And I always start my free body diagrams with all the applied loads, because that's like, I know that stuff, right? And then I worry about my reactions at my supports. Okay. So I kind of put everything that is known, points, all that kind of stuff. And then any dimensions as well. And that last dimension is 6 inches, if you're wondering. Okay. So I'll put mine underneath here and you can compare. So right now I'm not completely done yet, but as you can see, we've got all of the known forces, distances, and points along the length of that beam. So we've got our 15, 20, 35, 20, and 15. And then the 2 points of interest here for this problem, which are our supports, are going to be a pin connection at A. Actually put it to the side a little bit. A pin connection at A, which is right here underneath that 20-pound force. And then we also have a cable at BC, and the problem statement wants us to find the reaction at A and the tension in cable BC. So I still need to put my reactions at those 2 supports. So if A is a pin or a hinge, how many reactions am I expecting there? 2, right? Yep, 2. So I know that I'm going to have an X and a Y. So I'm just going to put these in here horizontally and vertically without my arrowheads yet. When I'm looking at putting my directions in place here, and I can kind of see right now I've got all forces that are going down. So a good chance for this to support and stay in equilibrium or to balance out, this is probably going to go up, right? So I'm going to show an arrowhead at A in the vertical direction as going up, and I'm going to call this AY. And then I need to also assume a direction for my X component. There are no other forces in the X that would be opposing this. So I'm just going to show it going to the right, and I'm going to label it AX. Okay. You do need to show that AX is going to be equal to 0. All right. So show it in there and calculate for it. Now, the other support that I have is at B. That's a cable. Okay. And if you need to, don't forget, you can always go back to page 160. And the cable is the second row here. The cable force is going to be one force along the line of the cable, pulling away from the body. So the body is that beam. And at B is where it's connected to the body. So this is going to be a vertical line. Oops. Vertical line. My arrowhead is going to go down. It's going to pull away from the body. And we're going to call this, well, they're calling it the tension in BC. So we'll call this BC. Okay. You could call it BY if you wanted to, but they're giving it a name. So now I have my reactions and I have all of my applied loads. I have all of my dimensions. And you'll notice here that I have 3 unknown forces. Okay. I've got AX, AY, and BC. So my next step then is to use my equations of equilibrium to solve for those 3 unknowns. And we know our equations of equilibrium are sum the forces in the X equals 0, sum the forces in the Y equals 0, and some moments, and I'm gonna put my little cloud here, you're gonna strategically pick a point, set those equal to 0 as well. Now that's as far as I want to go, but does anybody have any questions about the free body diagram or next steps? Okay. All right, good. So then, yeah, that's going to be the process that you take. Only 2 short steps. There's a couple little steps in between, but yeah. All right. So then let's look at our next problem. Our next problem is 4-7. 4-7. So 4-7. Oh, of course, these are out of order. There we go. 4-7 is found on the bottom of page 175. Okay, so it's down here. Now this problem, there's going to be 2 free body diagrams because they want you to find a range, but what you really do is you just set it in one position and then in another. So it says for the beam and the loading shown here, determine the range of the distance A. A is going to be our unknown here. We're not going to be solving for, well, we do solve for one force, but we're going to be also solving for a distance, which is a little bit different, but trust the math. It'll all work out. And it says that the reaction at B, which is right here, does not exceed 100 pounds going downward or 200 going upward. So we're going to draw it once with a force going downward as 100, and then a second time a force of 200 going upward at B. And then we'll solve for A 2 times. And then that's going to be the range that they're looking for this problem. Okay, so let's get the free body diagram in place first for each one of these situations. So the first one that I'm going to do is when B has a force on it that's going to be going 100 pounds downward. Okay, so I'm going to draw a line here. This is going to be problem 4.7, and I'm going to call it 4.7a because it's the first part. This is where B is going to be equal to 100 pounds going, downward. And we want to put our convention in place. So we're simply going to draw that beam. Okay. A 300. I'm going to draw this in between because I've got another element between. This is going to be 6 inches between those. And then it's going to be this distance lowercase a from the end. Okay. And then we've got point D right about here. And then we've got C right about there. Okay. So D, I'm going to put it on top, and then C, we have 50. There's that 50 pounds. Remember when I said, I know there's another problem that has 50 pounds going down at its geometric center, and that's point C here. Okay. And then out on the end is our B, okay? And in this case, B, we want to put in the downward direction at 100 pounds. Okay, 100 pounds. Now, distances wise, between these two, this is 12 inches. Put darker so you can see it. 12 inches, 6 inches between those. Then between C and D, bring this down here a little bit. This is 4 inches. Okay. And then to the end to A is 8 inches. Yeah. There's a lot of dimensions there. Now, we have a reaction at D as well. We have a reaction at D. D is a pin reaction. So we do need two forces at D. We need a vertical, okay, and we need a horizontal. So I'm just going to assume dy going up. And even though we don't have any x forces acting, and we probably already can predict what dx is going to be, we still need to label it, recognize it, and assume a direction, and then solve for it in your equations of equilibrium. So our unknowns here are dy, dx, and a. Okay, and a is a distance. A is a distance. Okay. Now, the approach I would probably take here, the approach that I would probably take for this is the first thing I would do is I would sum my forces in the y. My dy is the only unknown, or I would probably do x first to get dx out of the way. So sum your forces in the x equals 0 to solve for that dx, right? And then you're going to sum your forces then in the y direction, because your y is your only unknown in the y. Do you see that? So I'll be able to solve for dy under this equation right here, and that'll be to solve for dy. And then what you're going to do is you're going to sum a moment. Okay. And you're going to sum it around a point equal to 0 so that you can try to get that A. And I'm going to kind of let you chew on that a little bit. Okay. I'm going to let you chew on that a little bit. There's one point I think is easier to sum around. Huh? Does it what? Does it have what? Oh, sorry. I'm sorry. I didn't. Does it have seasoning? Now I know what you said. I don't know. But think about that. That's a little bit of a challenge. Now, any questions? You know, so we're not going outside of what we learned already. It's just that we're solving for a different variable rather than a force. We're solving for a distance. Okay. Now, any questions on the free body diagram? Okay. Let's draw the free body diagram for the second part. Now, the second part is going to be exactly the same as this, except we're going to have 200 going up. That's really going to be the only difference. So let's draw it just to be sure that you have what you need. And I'll put this one back up here if you want to look at that, if anybody's using this. Okay. And then just in case maybe you can't get the book open, or if you've been following along here, go ahead and draw the free body diagram for 4.7, and this is part B. This is where B is going to be going down. I'm sorry, it's going to be going up at 200 pounds. So B is equal to 200 pounds going up this time. And even if you don't get to solving these problems tonight, that's okay. This way, at least you've got some good diagrams that you can be confident in making progress independently. Okay, because it does, I mean, if you don't have good free body diagrams, you know, it's going to be hard to get good numbers. So this is probably the most important. You're going to put a dx and a dy at D because there's still that very same support. The numbers will be different though, because B changed. Okay, B changed. So I'm literally doing the exact same thing that I did last time, except B now is going up with 200 pounds. But everything else is the same. So I'll zoom out here a little bit. Don't forget your convention in the upper right-hand corner at the beginning of each problem. Okay, beginning of each problem. So as you can see, D going up is the only thing, I'm sorry, B. I always, usually B is on the end, right? Or D is on an end. There's B. Now it's going up. Last time it was going down. Okay, going up this time. And we still have dx and dy. There'll be, dy will be a different value. Dx will still be 0. And we're going to take that same approach where we're going to sum our forces in the x equals 0 to get your dx, okay? We're going to sum our forces in the y equals 0 to get dy. And then you're going to pick strategically a point to sum around, set that equal to 0, and your unknown then is going to be a, that distance, okay? All right. Any questions on that one? You might not see it just yet. That's okay. Just trust the process. Look for your unknowns and you'll algebraically, you'll see it come together. All right. Our next problem is 410, So I'm going to go and find where 410 is. Oh, this is a good one too. I like this problem. This one's 410. There's such a glare here. Here we have two lengths, AB and DE. AB is along here, okay? BE is going down here and they just kind of cut them off, okay? That are on this bell crank as shown. Knowing that the tension in link AB is 150 pounds. So that means if it's in tension, it's pulling away from B. Okay, it's pulling away from B, and that means that that force along that rod is 150 pounds. They want us to determine the tension in link DE, the force pulling down along that link, and the reaction at C. C is a pin. C is a pin. So what we're going to do is draw our free body diagram here too as well. And I want to make sure you've got that good so that then when you go to solve it using our equations of equilibrium, you've got good stuff to start out with. So I'm going to do this one with you because this one, it looks a little different. Normally I've been working with like straight beams, right? And this one is like fancy. It is fancy. Okay. All right. Scooch this up a little bit. So this is going to be 410. And I'm going to start with point C kind of like in my middle here. So I'm going to just draw a little crosshairs, and this is going to be my point C. Okay. I'll worry about the forces on it a little bit later. Now, I am going to draw a diagonal line going up to represent point D. Okay, up here. And then I'm going to draw another one a little bit shorter to represent going to B. Okay. And I'll put my convention so I don't forget. Okay. Now I do know that 90 degrees to that link, I do know that there's going to be a tensile force pulling away here. This is a 90-degree angle as shown in the diagram. And they call this a B. So I'm going to make that consistent with the problem. Then we also have another link, and they said it's in tension, and they're calling this one DE. DE. And then this is our point C. Now, the next thing we want to do, now we kind of have stuff in place. The next thing we want to do is add our distances, okay? Add our distances. So I'm going to go over and over. And this is going to be 4.5 inches. Okay, 4.5 inches. Then coming up, one going over to D is going to be 6 inches. Then over to B, it's going to be 4 inches. Okay. And then going up to B, I'm going to go through here and over. Like that. This distance is 3 inches. And that's from C up to B. C up to B. I think those are all my distances. So we don't know the length here. That's okay, but we do know how far over and how far it's up. Imagine that's going to be helpful. Now, any questions so far on this? Reactions at C. C is a pin, so it's going to have an X and a Y, right? So I'm going to show my CY. And I'm just going to take a stab and I'm going to put CX going to the right. It's usually my default, just because. Now AB is at that angle, right? Do you see how that's gonna need some components? Yeah. So I'm gonna kind of make a little right triangle here. This one's gonna come down. Are you guys happy when there's only vertical and horizontal forces in problems? You're like, but you're not afraid of components. Not afraid, it's just an extra step. You think they're scary? This is gonna be an ABX, right? Yeah. And an ABY. Now, do we know what oh, we do know AB is 150, right? 150. Is it pounds? Yeah. There we go. It is 150 pounds. So that's good. It's always nice when you have, and I think resolved numerical components. Yes.
For the forces at point C, would it matter if we had the arrowhead for CY going out instead of pointing into point C?
Which one? Oh, no, it's for CY? No. If you show it going down, or if you show it going up this way, oh, totally fine. Yes. Why? Why is that totally fine? If we, yes, Chris got it. The principle of transmissibility, you can move this anywhere along its line of action, and it is going to have the same net effect on the body. So if you show this starting here and pointing up, totally fine. Absolutely. Yeah. Good. Now, as you look here, your next steps, once we have our free body diagram all in place, we have our reactions of our supports identified, and we have all of our applied loads and our distances set. Now you're ready to use your equations of equilibrium. And you know what those are, right? You have everything you need here. Well, you have to resolve those X and Y's, but other than that, you're good. Any questions? I bet you're looking forward to doing this problem. I mean, I would. Like, I can't wait. So, so those are the first, I think, three problems, right, that you guys have. I'm gonna stop the recording right now. And then we'll look at some more.